The first question on the exam will be looking at a differential equation and identifying if it's a first order or what order it is, if it's a linear differential equation. If it's one of those first order differential equations that we've already discussed, then you can try to figure out if it's separable or if it's exact, or what substitution you might use to be able to find out. But you don't have to solve the whole differential equation. You might need to do some math to figure out whether the equation is exact or if it's separable. You might need to go through a couple of steps to figure that out. But in general, you don't have to solve for it. So don't waste your time solving for the first problem, because it's not there for you to solve. It's there for you to try to identify. I had some people last year solve for and then they didn't have time to do the rest of the test. So keep that in mind for the first one. The second one is a question where you have a differential equation and I give you the solution, and then you're asked to check if this is in fact the solution to the differential equation. So you need to show some work. I know in the homework they ask you questions like that, but you didn't really have to show any work. You just pick whichever differential equation or whichever solution looks like it works. But here I want to see the work to show that you took some derivatives and then you put it back into the differential equation to make sure that it's equal. And then based on that, I think I asked you a couple of initial value problems. So the same differential equation and same solution, general solution, you had to try to solve for the C to find a particular solution given the initial conditions or boundary conditions. Number 3 is modeling the differential equation. Now you had some modeling questions in 1.3, section 1.3, but most of the modeling questions are from section 3.1 or 3.2. So I think what I'm going to do here for question number 3 is I'm going to ask you a question that's similar to one of those problems in section 3.1, where you're going to try to model the differential equation and you actually go through and solve for the differential equation. And then as you solve for it, you follow it up with some explanations as to what each of those parameters mean, what the variables mean, and stuff like that. Number 4 would be kind of like most of the stuff that you did in Chapter 2, where you're solving for differential equations, separable, exact, first order, linear kind of differential equations. So you'll have between 2 to 4 problems. And then the last one would be focused more on section 2.5, I think, is when you did some substitutions. So we did some substitutions there to make something look separable, or substitutions to make something look like it's a first order linear. So you should be familiar with all those terms and all those types of differential equations that we've been working with. Sadie? You have to check. You have to check if it's homogeneous. You have to check. It might be a Bernoulli equation. You have to check one of those criteria. All right. I think that's it. 5 problems. 5 with multiple parts. Yeah.
So for the semester, we're going to have like 5 exams and then the midterm and the final.
5 problems?
For the semester, we're going to have like
2. You get 2 exams and then the final. What? Yeah, this is one test, and then you'll have another test, and then you'll have a final. Yeah. And I think I need to give you guys more quizzes, because quizzes are what kind of makes sure that you're up on things and you're understanding the material and stuff. And there's a couple of quizzes that I should have added, but I didn't. So I'll I'll try to give you a little bit more quizzes, and that'll help you kind of prepare for the exams. Anything else? Yeah, I'll let you know ahead of time. In fact, I'll probably try to see if I can get a schedule, a pattern, so that I can anticipate when the quizzes would be. All right, the first thing I was going to do was to go over some problems in 2.5 because it was suggested. And then after that, we'll do whatever we want. Leave early. What? Oh, yeah, you get one sheet of notes in your calculator. So in your sheet of notes, it might be good to include stuff like basic integrals or techniques of integration. You might need to do integration by parts. You might need to do some partial fractions. I tried. I don't think there are any trig substitutions in there, so I hope not. But if there is, then I hope you know it. So some of those basic things would be good, and of course maybe you might want to put an example of how to do a first-order linear differential equation in case you run into that, and then those substitutions. And maybe put a handful of application problems from section 3.1 that look interesting, or that might, maybe you'll hit one of them that might be on the test. Okay, so you get one sheet of notes, and you get your calculator. Now, I understand some of these calculators, the TI-89, they can actually solve for differential equations. They can solve for integrals analytically, symbolically. But I actually would still like to see the work that's involved in doing it. So, for example, if you're doing a first-order linear differential equation, you're looking for the integrating factor. And so I need you to find the integrating factor for you before you put that in the final answer. So I'm not too keen on just, have no work at all and then the final answer. That's not what I would like to see. I'd like to see the steps to get to that final answer. Okay? All right. So let's go to section 2.5, and we can randomly pick a number here and do one of these problems. Any particular ones? What? 3? This one? Looks good. The thing about some of these problems is that if you're not fresh on it, you could take a really long time solving for one problem. Unfortunately, there's 6 to 8 differential equations that you have to solve on this test, and you can spend for any one of them, you can spend the whole time. And the idea is to prime yourself. So this is almost like a test-taking strategy. To be able to successfully complete this test, it's almost like a question of test-taking strategy rather than knowledge of differential equations, which is kind of unfortunate, but that's the way we test, and so that's how it goes. So the idea is that when you look at this, you have to know the steps that you need to take to do this, because if you fuddle around and try to look for it in your sheet and you can't find it because you wrote too small or something, then it's going to eat up a lot of your time. So it's really important that when you look at this and say, oh, this is a homogeneous differential equation, I'll look at my homogeneous differential equation part of my notes and says, oh, okay, this is what I have to do. I have to let y equal to, or u equal to yx or something, and then move on. And you got to move quickly because you got to finish the test in time. All right. So this is a homogeneous differential equation. How would you know this is homogeneous? What is a homogeneous differential equation? Degree is the same. Degree of what, though? It's what? X? X and Y. The degrees of X and Y are the same. They kind of look the same here. So I guess before we assume that this is a homogeneous, it says it's homogeneous, like Sadie was saying. I'm not going to do this on the test. I'm just going to give you a differential equation. You have to run through your own notes to figure out what it is. And so the way I would think about this is that, first of all, can I separate this? I can't separate it because there's an x cubed, y cubed that's being added or subtracted, and so they can't be torn apart away from each other. It's not separable. Is it first order? Yes. Is it linear? Y is taken to the second, third power, so it's not linear. Okay, done with that. It's not a first order linear, so now it's one of those possible substitutions. Now we took a look at 3 substitution types in this section. One of them is homogeneous. The other one is a Bernoulli differential equation. And then the last type is one of those that look like an ax plus by plus c or something like that. If you can take that whole term and substitute it, then that's how you work. That's how it might work out. So by looking at this, if I run through that set, this looks like it might be homogeneous. If I'm not entirely convinced right away, my second thing is to check if it's a Bernoulli equation. And it doesn't look like a Bernoulli equation because there's a y cubed and a y squared. And according to Bernoulli, it kind of looks almost linear, except the right-hand side has a y to some power. So I know it's not Bernoulli. And because this is raised to the cube, to the third power, I know it's not an ax plus by plus c kind of substitution. So I didn't think it might be homogeneous, but let's go back and actually check if it is homogeneous. So how do you check if it's homogeneous? Don't you need to separate it, like to see if, make it look like the exact equations, right? So dx and dy separated. All right, so let's do that. Let's take this and separate the dx and the dy. So it's x, y squared, dy is equal to y cubed minus x cubed dx. And I can move everything to one side, or I can just stop here and say, okay, I need to figure out what do you call it? The powers or whatever. So if I take this and then put t in for x, or tx in for x, and ty in for y, am I going to get something with a t in it that's factored out? So if I factor out a t cubed, I don't really factor it out. I just associatively move it around. So I have my original function, x, y squared, and then my homogeneous power is 3. So I have to match a homogeneous power for this one as well. So to check that, I would replace the y's with ty, replace the x's with tx, and then after I do that, I see, oh, this is t cubed, the same t, the same power t, times the original thing. Okay? So I know it is homogeneous, and that's the way to check if it's homogeneous, if they didn't tell you it's homogeneous. All right, now that we know it's homogeneous, we go ahead and do the substitution that they suggest for homogeneous differential equations. And the substitution, it's either x or y. I think y is equal to u times x or something. And then let's deal with differentials. I'm kind of tempted to deal with this as dy dx, because dy dx is sitting here by itself. Let's try that. So this is x. This is an independent variable. This is u as a function of x. and then this is y as a function of x. So the derivative dy dx is, we still have to use the product rule. Derivative of the first times the second. The derivative of x is 1. No, it's just, I'm not taking the derivative of the second. Derivative of the first times the second plus the first times the derivative of the second. Now it's 1. No, this is the product rule. That's what you meant to say, right? Yeah. This is the product rule. Derivative of the first times second. But but what I'm doing is I'm treating y and u as a function of x, and x is just equal to x. So that's your variable. So that's how I got what I got. And then I'll do the substitution here and get rid of all the y's. So let's see. I have x, and then I have u times x to the second power. And then dy dx is this whole big mess. This is x times du dx plus u. Is equal to, now I'm going to replace this with a u times x to the third power minus x to the third power. Right? So by the way, when you're working with a homogeneous differential equation and you do substitution, what should you expect to eventually get? A what? You should expect to get a separable differential equation, right? The Bernoulli substitution, when you do that, you should expect to get a first order linear differential equation. So it all kind of bounces back to that stuff at the beginning of chapter 2. All right, let's multiply things out here. I'm going to have u squared. This is x cubed plus another x. That's x to the fourth total du dx plus u squared times u. That's u cubed x cubed is equal to u cubed x cubed minus x to the third. Now, I was going to factor out an x to the third on the right-hand side, but good thing I didn't, because I see that these two are in common on either side of the equal sign, so they would just go away. And again, we should be expecting a separable differential equation, so I think that's coming soon. I have, well, let's make it show up now. I have u squared du, and then I'll divide by an x to the fourth. That will give me a negative x in the denominator, and then a dx regular. Did I do that correctly? Maybe you guys should double check. A couple of nods would make me go on. I got 2 nods. All right, we're moving on. And so now you just integrate. So the integral of each of these things, these negative signs. Remember that one negative sign that I missed and threw off my whole deal? So we'll start off with u cubed over 3, and the plus c there will just merge with the plus c on the other side when we come up with that plus c. So we have a negative. This is an ln of x, and then let's throw in the plus c. So you can solve for the u right now, but we need to change it back in terms of y's, right? So y is equal to u times x, so that means u is equal to y over x. So 1/3 y over x to the third is equal to negative ln of x plus c, and then solve for y from here. Oh, 3x cubed, then you take the third root, right?
Would that still be, can that be merged into C?
No, because you're multiplying, dividing, and stuff. When you multiply, divide, you multiply, divide the whole thing. So I would just leave it out. So I think y is equal to 3x, and you're taking the third root of that, so that disappears too, but you're taking the third root of everything else. What? Sure. Yeah. And then, no. I was going to switch the c and the ln x just to write as c minus ln x. So keep the negative in there. Maybe? The what? Cube root. What? Oh, 3 should be inside. Yeah. All right. Okay, now we put 1 in for x and y. According to the initial conditions, and solve for c. Let's see what happens there. We got 1, 1. We got the cube root of 3c minus ln of 1 is 0. So that just goes away. So c becomes negative cube root, or 1 over cube root of 3. Is that right? No. You have to cube both sides, and then so just 3, or 1/3. 1/3. All right. Let's see if this is the correct answer. So 3 1/3 minus ln x. They didn't have a y equals to here, which means we could have left it as implicit, I guess. So y equals x times, should we do just to the 1/3 power? It looks like 1 minus 3 ln x. Why is this not highlighted? Raised to the 1/3 power. Oh, it looks good. That worked out. Yeah. So the last problem, which is the one of those substitutions, I think you'll have two problems. So it's either a homogeneous or Bernoulli or a linear ax plus by plus c substitution. But yeah, I'm not going to tell you which one it is. You just have to figure it out. Yeah, but I'm not going to tell you it's homogeneous. I'll just say solve for this using substitution. If I do, I don't know if I did. If I do, then you know it's homogeneous. Then you just move on. All right. Should we do another problem from this section? Or a Bernoulli? Here, it says this dE is a Bernoulli equation. Oh, number 5? This is a Bernoulli equation. Let's do number 5. Okay, so how do you check if it's a Bernoulli? It's not too obvious right now, and in fact, you won't know what the n is unless you write it into that specific form, the Bernoulli form that they're looking for. So to write it into a Bernoulli form, remember, a Bernoulli form looks almost like a linear differential equation, except the last term on the other side of the equal sign has a y to some power. So if we distribute the y's, x, y to the 7th minus y, and then bring the y term over to the other side, you should expect the y term. So dy dx plus y is equal to x times y to the 7th. Now you are looking at the Bernoulli form. So this is Bernoulli, your p of x is 1, your q of x is equal to x. Not like it's going to matter now because you're going to change the whole form anyways. But the most important part is that you identify your n. N is equal to 7. Okay, we wouldn't have seen that from the beginning unless we wrote it into a Bernoulli form, and that would be just a way to check that it's Bernoulli. Oh, first, you would probably look at the differential equation and say, okay, it's not separable, and when you work it out like this, it's not a first order differential equation. But by the time you write it like this, you would know that it's not, it is a Bernoulli, it is in fact a Bernoulli equation, and you won't have to check if it's homogeneous or anything else because you're just, if it's a Bernoulli equation, that's what you're going to do. All right. Now that you know it's a Bernoulli equation, you're going to do a substitution. And the y substitution is, what was it? 1 minus n or something like that? So your substitution for a Bernoulli equation is a u equals y minus n. It should be negative 6, right? Is that better? Does that look okay? All right, and so you have a bunch of y's to replace. You're going to replace a bunch of y's in there, so you're going to need to figure out what y is equal to. Y is equal to u to the, how does the power go? Is it negative, is it positive 6 or is it negative 1/6? It's just algebra. What is it? One-sixth? If it's a 1/6, it has to be negative, right? Negative 1/6. So just take both sides to the power negative 1/6. There'll be y to the first, and then u to the negative 1/6. All right, you also need to replace the dy dx, and so y is a function of x, and u is a function of x. And so the power goes down, you subtract 1, so it's negative 1/6 minus 1, negative 7/6. Right? Whatever happens here, when you do your substitution, your differential equation should eventually look like a first order linear in terms of u. So if that doesn't work out, then you might have done something wrong in the meantime. So let's see it become that first order linear differential equation in u. So dy dx is negative 1/6 u to the negative 7/6 du dx plus a u or a y, which is u to the negative 1/6, is equal to x times u to the negative 7/6. Right? I replace y with u. This is u to the negative 1/6 raised to the 7th, so you multiply the powers and you get that. So this is where the magic happens. This divided by all the way through, and then we'll throw a divided by negative 1/6, so we're multiplying by negative 1/6. So du dx, so it gets multiplied by negative 6, and this becomes a u, right? Negative 1/6 plus 7/6 is equal to x times negative 6. Okay? There you go. Now it's a first order. U is the dependent variable. It's the first order in U. And then the x is the independent variable. So whatever this is on the right-hand side, it doesn't matter, as long as the u's raised to the first power, and then we're all good. Now we got a first order linear differential equation. We would be looking for an integrating factor here. Mu is e to the coefficient. The p of x is negative 6. So that's just e to the negative 6, right? Or e to the negative 6x. That's your integrating factor. And if you're not comfortable with this step that I'm going to skip, I want to make sure that you actually write it down a couple of times and read through the book again and look at the example for doing a first order linear differential equation. But what happens here is that you multiply by the integrating factor, the left-hand side will become a product rule of two things, and the two things that it's a product rule of is negative e to the negative 6x times u. And as this is a product rule, you undo the derivative, and so you take the integral of both sides, and then you have negative 6x e to the negative 6x dx. So we'll have to do an integration by parts problem here, which you guys are all experts on. U is negative 6x, dv is e to the negative 6x dx, du is equal to negative 6 dx, and v is equal to negative 1/6 e to the negative 6x. So uv, the negative 6's would cancel. I have x e to the negative 6x minus v, the integral of v du. Negative, negative would cancel. The 6 and the 6, 1 6 would cancel. Also, and I just have an e to the negative 6x dx. Remember this? This used to be fun. Just a simple integration by parts problem. Now we have to do all kinds of other differential equations crap. So the antiderivative of this, we already did this. This is going to be negative. Let's make that into a positive 1 6 e to the negative 6x. And then let's throw in a plus c. Two more steps. Whoops. First step is to multiply both sides by e to the negative 6x so that we get u by itself. And so the negative 6x would cancel. We have an x plus 1 6 plus c e to the negative 6x. Transient term. Right? So this graph, whatever it's going to look like, it'll be approaching this line x. Oh, positive? Okay. Then it's not a transient term. And then we still need to change this back in terms of y. So we got y to the negative 6 is equal to all this big mess. And then just undo it. So how's that go? Negative 1 6 power? Right? Is it negative 1 6? Okay. What? Check the answer. All right. Oh boy. Y equals big parentheses x 1 6. All right. Looks good. Good thing we have this answer check, huh? In case you don't trust your teacher. All right, are we good? Do we need to talk about anything else? Are we done? We'll be done. Let's be done. Unless you want to talk about anything else. Any other issues with the homework problems or anything you might have run into? So you really have to know the first order linear differential equation. The separable stuff, separate it, and then you just have to look back at your Calc 2 skills and try to be able to solve for those and identify things. Let me take a look at some problems from the review. Where's the review? Want to just shout out a couple of these things, or should we actually put it in our notes? Notes that you guys don't even look at. All right. Let's do a couple of these first, since I already started. Okay, let's take a look at the first one. What's the order? Second order. If it's second order, at this point, the only other thing to check if it's linear or if it's not linear, because we don't have any other techniques in the thing. So is it linear or not linear? It is linear. All the y's your dependent variable, and there's nothing being done to the y's or y primes or double primes, so this is a linear. So this is second order and linear. And like I said, there's no, we can't check Bernoulli or homogeneous for these things, so we're kind of done here. Let's look at this one. What order is this? This is first order linear. So if it's first order, we know it's linear. Can we also check if it's separable? Is it separable?
Yeah.
I'd like to see you try. Try to separate it. So dy dx equals, or plus 3y is equal to sine x. So there's a plus 3 here, so we can't separate it. So it's not separable. Because the sign is you can do whatever you want with the independent variable x, but as long as the dependent variables are not being put. If this has a sign y, then it's not linear. But if it's the x that's signed, then that's okay. In fact, instead of a 3 here, you could have had a cosine x or something else. As long as it's just an x in there, then it would still be linear. Still be okay. So if it's first order linear, then we don't have to worry about trying to find Bernoulli or anything like that, because if you've already identified it as first order linear, then you should be able to solve for it with an integrating factor. All right. Modeling. Somebody want to do a modeling problem? Are there any modeling problems here in the sheet? You guys should know how exact equations too, right? Logistic problem. Here they kind of give you the differential equation already. All right, 26, 27. We did like a 27 problem before, didn't we? This seems to be a simple one. Let's do it anyway. So the idea is that it's a modeling problem. So what you need to do is be able to look at the words and translate the words into a differential equation, and then eventually be able to solve for it. So bacteria doubles in size in 8 hours. How long will it take for a size to triple? Assume the rate of increase. So these are the words that gets translated. The rate of increase, that's d something dt, of a culture is proportional to the size, the current size. Okay, so those are the key words. So rate of increase, let's call this A or something, dA dt, is proportional to its size. Okay? So that's how the translation happens. And just try to pick out the words and translate it directly. So proportional is saying it's equal to k times something, alpha times something. And that's it. So this is our differential equation. We don't have an initial condition, and this first piece of information that they give us, doubles in size in 8 hours, will help us solve for k. So there's no initial condition here. You have to be careful how you solve for this thing. It doesn't look like there's an initial condition. If we saw something like the initial Petri dish had 10,000 bacteria, then we know that that's going to be your initial condition. But there's nothing like that here, so we'll see how or what happens to the initial condition. All right, let's solve for this differential equation. This is a separable differential equation. dA is equal to dA over A is equal to KT dt, something like that. And then I'll take the integral, ln A is equal to KT plus C. A is equal to, I'm going to put A naught for the e to the C constant. So it'd be nice if we can solve for this. So because there's no initial condition, can't solve for A naught. So hopefully we don't need that actual value when we work things out. Let's try to answer the question. The question is, well, before we answer the question, let's use this information to help us solve for k. So A of 8, it doubles in 8 hours. So if we had A naught to begin with, A of 8 should equal to 2 times A naught, right? And then this is going to be equal to A naught e to the k times t, which we said was 8 hours. And if you see this work out, the A naughts are actually not very important in this case. If we're just talking about having this thing double or triple or anything, it's independent of the size of the original function, so, or the original bacteria. And so we solve for k. So we'll take the ln of both sides and then divide by 8. And then we get whatever we get there, and then we'll put that back into the original equation, or into the equation that we found. And then they asked us when is this going to triple. So when is it going to triple? We're going to set this equal to 3 times the original amount. And then solve for t. And And again, the A naughts cancel, and then we're just left to solve for t. So whatever that turns out to be. Okay? And it is an actual number. And again, we didn't need to know the original size of the bacteria, so we're all good here. So the trickiest part in this modeling is coming up with this differential equation, and that's your task. After you do that, I hope the differential equation is easy enough for us to solve, for you to solve, and then you go through the work and find any parameters that are missing, and then answer a question like how long it's going to take to double or triple or something like that. Or how much bacteria is left after 4 hours. Of course, if I asked you that question, you would need to know what A is equal to, or A naught, the original. All right, anything else? Got 5 more minutes. Let's end early and go to the STEM Center. Coffee and donuts that aren't there. Okay, so I think if you focus on Chapter 2, the bulk of the test will be on Chapter 2. You know, the last 2 problems will be actually solving for problems. If you focus on Chapter 2 and know how to do the first order linear differential equations, know how to do those 3 substitution problems, then you should be really good. Okay? And you have to do them quickly, right? You can mull over a problem, but if you mull over a problem for 15 minutes, then that's 15 minutes of lost time. You got to look up a problem and then just dive into it. Nick, question?
You said there's going to be an exact result of the
Yeah, so that kind of falls under the category of the separable, the first order, and exact. So those are in their own sections. And then the last section, or second to last section in Chapter 2 was the 3 substitutions. Okay. All right. Good luck. I want you guys all to go to the STEM Center. If you go, they're doing that passport thing, right? If you go do that passport thing and bring it back to me, I'll give you 1 extra point on the test on Thursday. Do you have the passport? Oh, you need to get it. You need the passport. It's over there. I don't know. They're playing games or something like that. So go there, just hear people talk, and then get things signed, and then bring it to me. I'll give you a point.
Bring it to you on Thursday?
On Thursday for the test.